you for this opportunity. Today I want to talk to you a little bit about our work on facile size-selective defect sealing in large area atomically thin membranes for sub-nanometer scale separation. I'm Professor Piran Kidambi at the Vanderbilt University at the Department of Chemical and Biomolecular Engineering. Before we proceed further, I want to give you a quick introduction of the mechanisms of transport in membranes. What you see here in this x-axis is a length scale in terms of molecular diameters, and this is in relation to the pore size in membranes. At the angstrom or sub-nanometer scale, a lot of membranes operate in this realm for gas separation, which operates on a mechanism of solution diffusion, where the flux through the membrane is proportional to the diffusivity times the solubility. In other words, molecules initially solubilize into the membrane material and then diffuse through the membrane material to emerge from the other side. So the product of diffusivity times solubility then dictates the amount of separation you get. If you increase the molecular size slightly, you get into a regime where you have molecular sieving. In molecular sieving, smaller molecules are able to get through the pores in the membrane, whereas larger molecules are retained. This is what we're going to be talking about later today. If you increase the size a little bit further, you get into the Knudsen diffusion, where the flux is inversely proportional to the square root of the mass of the material being separated. If you increase the size of the pore even further in membranes, essentially what you get is postural flow or pipe flow, where the flux is proportional to 1 over the viscosity of the fluid. On the bottom end, then you have liquids. In liquid phase separation, you can have either solution diffusion identical to gas phase, or you can have separation based on charge or affinity as you increase the size a little bit further. As you increase the size even a little bit more further, what you end up with is particle filtration, where effectively larger particles are being retained, whereas smaller particles are able to get through. On the right-hand side, I show you on the y-axis selective layer thickness, and on the x-axis, I show you the structure. Conventional reverse osmosis polyamide membrane for water desalination purification sits somewhere here, where the thickness is on the order of a few microns, and they're extremely disordered in structure. Anodic alumina membranes, on the other end, are extremely ordered structure, but they are still relatively thick. What I'm going to talk to you today about is nanoporous atomically thin membranes, where the structure is extremely ordered in the sense that you only have one atomic layer and you're then making nanopores in this single atomic layer to enable separation. In other words, we're going to talk about length scales in the angstrom in terms of selective layer thickness and extremely ordered structure. So let's look at how we fabricate some of these membranes. And keep in mind, the challenge for desalination is how do you make trillions of holes with a pore size between 0.3 and 0.6 nanometers? How do you make trillions of these holes that are all the same size with very high density per centimeter square? So that's the grand challenge, because the molecule of water is around 0.28 nanometers in size, and salt is around 0.6 to 0.7 nanometers in size, hydrated diameter of individual ions in salt. So what we do is we take graphene grown via chemical vapor deposition on copper foil at a reduced temperature, which allows us to nucleate defects in the graphene. We press this graphene against polycarbonate track etch membranes. These polycarbonate track etch membranes have perfect cylindrical pores throughout the membrane with 10% porosity, and these pores are around 200 nanometers in diameter. We then etch away the copper from underneath. This leaves graphene transferred to polycarbonate track etch supports. We then come in with a UV ozone process, where we are introducing sub-nanometer pores in the graphene lattice, as well as growing additional pores. And finally, we do our size-selective interfacial polymerization, where we only plug out defects that are larger than the size of water molecules while preserving sub-nanometer scale defects that allow transport of water molecules. This is what the optical image of one of these fabricated membranes look like. An SEM image shows graphene covering vast regions of this polycarbonate track-edge membrane with these pores. You do see some damage in some open pores. I'll talk about how you seal them in a bit. A zoomed in further image actually shows you these clear, nice 200 nanometer pores covered with graphene. That's why they appear darker. When they're not covered with graphene, they charge and they look brighter. Now, the key aspect of our size-selective defect sealing process is to take this graphene on polycarbonate track-edge membrane and sandwich it between an aqueous phase. In the aqueous phase, we have POS. This is octa-ammonium POS. And this has a central cage that is around 0.5 nanometers in diameter. On the organic phase, we have TMC, or trimethyl chloride. And trimethyl chloride dissociates in the aqueous phase. So trimethyl chloride cannot be stable in the aqueous phase. So in other words, the reaction between trimethyl chloride and POS is pinned at this interface that's behind the graphene in the organic phase, because the POS has to diffuse through defects in the graphene and made the trimethyl chloride to actually form polymerization on the other side of the membrane. This, in effect, allows us to preserve these small nanopores in the graphene membrane, because these small nanopores will not allow the transport of POS, but will allow the transport of water. So this is how we preserve the small nanopores in graphene while sealing away any large pores that may allow the transport of salt. Salt is around greater than 0.66 nanometers. So we pick POS, which is exactly around 0.5 nanometers, cage size, that allows us to selectively seal any large nanopores, as well as any open tears or any other damages like you see in these SEM images that are caused from the mechanical pressing process of graphene onto the polycarbonate track-edge membranes. We then sandwich these membranes into a side-by-side diffusion cell, which has a stem that allows us to do hydrostatic pressure-driven flow experiments, as well as osmotic pressure-driven flow experiments, while quantifying the amount of solvent that goes between these two reservoirs. We simply use three or four different kind of analytes. In this case, we use potassium chloride salt. Hydrated diameters for both of them are around 0.66 nanometers. We also use sodium chloride, where sodium hydrated diameter is around 0.7 nanometers. Use L-tryptophan, which is around 0.7 to 0.9 nanometers, and vitamin B12, which is around 1 to 1.5 nanometers. In addition to that, we're leveraging simple scaling laws, where in pressure-driven flow scales as d raised to 4 over L, and diffusion-driven flow scales as d squared over L. And the key aspect we're going to be looking at is diffusion, which allows us to probe defects that are less than 1 nanometer. So let's characterize some of the sub-nanometer scale defects that we introduce into graphene. What we instantly see is, with increasing UV ozone etch times, we're basically damaging graphene. As you see, here is the graphene that we initially made, and we basically then are continuously damaging, which is characterized by this increase in the D peak in the Raman spectra of graphene. Now, we transition between a low-density defect regime to a high-density defect regime with increasing UV ozone times as extracted from the ID to IG ratio, and then we can calculate the interspacing between the defects. In addition, the full width at half maximum of the 2D peak also continuously increases with increasing UV ozone time. What we then do is we then take these membranes and we effectively measure diffusion through them after interfacial polymerization. So initially here you see diffusion measured just on the nanoporous graphene on polycarbonate track-edge supports. After IP, what you're seeing is basically all of the analyte flows basically drops. This is primarily only for the polycarbonate track-edge membrane with interfacial polymerization. When you take the graphene that's been then, when you take the polycarbonate track-edge membrane and then only do UV ozone treatment on it. Now, this is without graphene, and then do interfacial polymerization on it. This resembles the polycarbonate crack etch membrane that was initially only treated to interfacial polymerization. So effectively, nothing changes on the support due to UV ozone treatment. But then when you take graphene after interfacial polymerization, you basically consistently see with increasing amounts of UV ozone etch time, you're increasingly then seeing an increase in KCl flux, but you're not typically seeing an increase in LZ or B12 flux. What happens surprisingly is that at around 25 minutes, this increase in flux suddenly drops. And this is the region where we think is we've now grown these pores large enough that they allow the transport of POS, and this allows POS to block some of these plugs, which allows us to get membranes that that only allow water transport but don't allow for salt transport, as I'll talk to you in the next couple of slides. We can also then characterize these pore densities based on extensive STEM imaging. So STEM imaging allows us to visualize these really tiny nanopores or really tiny sub-nanometer pores in the graphene lattice. We can also pick up the sub-nanometer pores formed directly on the copper when the graphene is on the copper. And this is what we see from these STM images. Now, let's go ahead and proceed and evaluate the performance of these atomically thin membranes. What we typically see is the water flux increases with increasing amounts of UV ozone treatment, as we expect. Typically, what we're seeing is with increasing UV ozone time, we're seeing increasing water flux. Interestingly, the salt transport is typically very low. What you see here is the rejection is typically very high, which means the transport is very low. And particularly for about 25 minutes of UV ozone, we get the lowest amount of salt transport or the highest amount of salt rejection, while allowing very high water flux, as can be seen here. So these brown stars is what we're looking at. So we get an optimum between water transport as well as very high salt rejection. And keep in mind for LTR, which is around 0.7 to 0.9 nanometers, we're getting 100% rejection. Likewise for B12 as well. So one can plot the water permeance as a function of solute rejection, and what we're typically looking at is we're looking at these star-shaped symbols. This tells you that the 25-minute UV ozone treatment before interfacial polymerization allows us to make really nice sub-nanometer pores that only allow for water transport but are not allowing for salt transport, or in other words, they're giving very high salt rejection. The salt rejection between two membranes can also be compared. For example, here we're comparing a nanoporous graphene membrane that's been treated with 20 minutes of UV ozone with 25 minutes of UV ozone, and we see that 25 minutes is slightly better in terms of in terms of solute rejection. And typically, with increase in solute diameter, you get higher rejection. Finally, we compare the water permeance that we obtain from these membranes with salt rejection compared to all the other reports that exist in literature, and this surpasses most other work in the literature on this topic. So in other words, our technique actually allows us to make membranes that typically allow for very high water permeance while allowing excellent salt rejection. We now wanted to see if we can do this with pristine graphene, because all of this so far all of the results that we obtained here was on graphene grown at 900 degrees C, which is what I meant by low temperature graphene. So here, instead of doing instead of taking pre-engineered defects in the graphene lattice, we started with pristine regions of graphene, and that's why the graphene here initially, the starting material has no D peak. And with increasing UV ozone time, you typically see an increase in the D peak, which means you're forming defects in the graphene lattice, as you can see here from the STEM image. However, the water flux that we obtain and the corresponding salt rejection with regards to when we make membranes from pristine graphene is slightly lower compared to when we are using graphene that has pre-engineered sub-nanometer scale defects in it, primarily from low temperature synthesis. That brings me to the end of this talk. What I've shown you today is we can engineer precise size-selective defects in the graphene membrane with very, very close tolerances. That is, the defects are slightly larger than 0.28 nanometer, which is the van der Waals diameter for water, while being smaller than 0.66 nanometers, which is the size of the hydrated diameter of potassium chlorine and potassium chloride ions. This is possible by a simple novel interfacial polymerization process where we use POS to just simply block out defects that are beyond 0.5 nanometers, because the POS cage size will be able to transport through the graphene, meet TMC on the other side, and effectively seal all of these defects. It will not be able to go through defects that are less than 0.5 nanometers, allowing these defects to stay open. With this, we are able to reach performance that surpasses nearly all of the membranes published in literature. So the key aspect here is we get very high water permeance while maintaining very, very high salt rejection. With that, thank you very much for your attention. I want to acknowledge all these people who did all the work and all the funding sources. I'd be more than happy to take any questions, and you can also reach out to me via my email. Thank you very much. Once again, I really appreciate this opportunity.